Is our next speaker. Leonardo Grigorio. He is now in École Normale in Lyon, and he is also from Brazil, from Nova Friburgo. So Leonardo will be talking about instantons in the Lagrangian model of turbulence.
Thank you, Alexei. Thank you, Luca, as well, the organizers. It's a pleasure to be here. And this work has been developed at the École Normale Supérieure with collaboration with Freddy Bouchet, Rodrigo Pereira, and also Laurent Cheviard. It's basically an application of the large fluctuation, of a large fluctuation tool in a model of turbulence. Right, so this is the plan of the talk. After a motivation, I will introduce you the recent fluid deformation model. In the second, I will apply some large fluctuation techniques in this model, discussing the results, and at the end, some final comments. So, large fluctuations are commonplace in turbulence. And here I'm showing a PDF of velocity increments at different Reynolds numbers. And in comparison, it's also plotted here a Gaussian PDF. And we see that large excursions are very probable, you're much more likely to observe large fluctuations of the velocity field in comparison with the Gaussian profile, since you are looking at the small scales of motion. And this is usually called a manifestation of intermittency in turbulence. And another manifestation of intermittency can be seen if you look at the structure functions of turbulence. Provided that we are at the inertial range, I mean, if we are far from the largest scales and far from the smallest scales, here eta is the Kolmogorov length scale. If you are in this range, the Kolmogorov theory predicts that the structure function scales with distance as a power p over the structure function of order p is p over 3. And this assumption required to deduce this, you need isotropy and homogeneity, and you also assume that the dissipation rate is constant. But what is observed, however, is that the coefficients are a bit different from the K41. Right? And as proposed by Landau, the reason for that might be that the presence of fluctuations or the velocity gradient can play a significant role, and so that you cannot assume that epsilon here is constant. Right? So the fluctuations that happens at small scales or at the velocity gradient is a significant thing to look at for the fundamentals of turbulence. So this is a motivation of my talk. And okay, so velocity gradients are a very natural candidate since they naturally probe the small scales of motion. And so if we take the gradient of the Navier-Stokes equation, we end up with this equation where A is the velocity gradient tensor. And incompressibility imposes that this tensor must be traceless. Right? Well, if you want to study the statistics, we have a problem because this equation is not closed. And we need to resort to models. You have to give a prescription, you have to provide a model in order to write this equation properly. And there are many attempts to modeling the velocity gradient Navier-Stokes. Basically, the model that I'm talking today belongs to a class that we assume that we are looking at the velocity gradient across the velocity gradient surrounding a particle around a Lagrangian trajectory. This is a very common approach in the literature. For a review, I suggest the paper of Meneveau, right? So in this approach, there's a huge weakness that we are not trying to describe the whole velocity field. We cannot talk about anything about the velocity field that drives this particle. We're just looking at the velocity gradient surrounding this particle. And of course, we have to model local and non-local interactions that acts in this particle. Well, one of the simplest models that we can write is called the restricted Euler, and we basically neglect the viscosity and neglect also the non-local effects of the pressure, so that we can write the pressure Hessian in a diagonal form. So this is the simplest thing we can do. And within this approach, the equation is closed. And this model displays some interesting features as the vorticity alignment and axisymmetric extension. One of the drawbacks, however, is that a singularity arises. The velocity gradient blows up at a finite time. Okay, and the model I'm working with was proposed by Laurent Cheviat, and it's basically a way to incorporate the pressure effects and viscosity in order to regularize the solution. Okay? Well, the rationale goes as follows. We take the pressure Hessian and we do a change of variables from Eulerian to Lagrangian coordinates. So, right? So capital X denotes the Lagrangian coordinates, small x denotes the Eulerian coordinates. And this is basically the Jacobian of the transformation. And of course, we are neglecting variations of the Jacobian. And this is an approximation. The Cauchy-Green tensor is the product of the Jacobian. And in this model, it's assumed that the pressure Hessian in the Lagrangian coordinates is isotropic, so that you can write in a diagonal form. With this prescription, we can write the original pressure Hessian in that form that depends on the Cauchy-Green tensor, right? And the reason for the motivation for that is that if you look at the initial configuration of the particle, assume that the pressure Hessian is isotropic here is the same as assume that in a time in the past, when the Lagrangian and at the initial time where the Eulerian and Lagrangian coordinates are equal, we are assuming that in this state, this blob of particle of fluid was isotropic. So, which is at least more reasonable than supposing that it's isotropic during the whole trajectory, right? But of course, it's still ad hoc. Right, the viscous term is modeled in the very same way. We go to the Lagrangian coordinates. We assume that this Laplacian can be written in a diagonal form. And we also use these NZs, that the derivative of A with respect to capital A, the second derivative, can be written like as a linear damping. And capital T is an integral time scale. It was, this idea was taken from this paper. Is a way to achieve a closure for the viscous term. Thus, if you put all together, this is the expression of the evolution of the velocity gradient, right? The second term on the right hand is the pressure term. The last one is the viscous term. But now the equation is closed. A is written just in terms of A at the same point. So we are basically modeling the effects of the turbulence surrounding this particle by the Cauchy-Green tensor that way. It's also assumed that the evolution of the Cauchy-Green tensor, instead of being solved, is prescribed by that, motivated by the fact that the velocity gradient is short-time correlated. And tau, here is the Kolmogorov time scale, is the short time scale. And the dependence on Reynolds number in this model is given by the ratio of the Kolmogorov time scale and the integral time scale. In order to obtain stationarity, we have to add a stochastic force, to add a force that we are adding a stochastic, and we assume that is white noise in time and has a tensor structure like that. Here's the Dirac delta function, and G is a fourth order tensor, and isotropy requires that it must have this form. And small g here is the strength of the force, and is proportional to the energy injection rate to the fluid. Actually, g squared is proportional to the energy injection rate. Well, the question we want to address is that what is the conditional probability of finding the event, let's say A12, at a final time equals to A, provided that the initial configuration was that the velocity gradient at minus T0 was 0. So we evolved to a state that is asymptotically going to 0 at minus infinity, and we are looking for situations that one component of the velocity gradient assumes a certain value. I'd like to highlight that we are not setting the fully state here. I mean, we are letting free all the 8 degrees of freedom, but we are just setting one value of the velocity gradient, right?
Why? Why you pick only one value, not the whole matrix?
Well, to do this approach is this algorithm. Apparently, it works better in this case, but it can be motivated. For instance, if you are looking at a large fluctuation of some, let's say the Burgers equation, and you are usually interested in the high values of the velocity gradient. So what you do is that, okay, I put a constraint on the velocity gradient, but since I'm looking at the velocity gradient, so I don't need to give the full final u, just the velocity gradient. But there are also technical reasons for that. Okay.
Actually, the reason is that it's the question we're asking. The question is what's the probability of getting A12 equal to A? So we cannot fix the other components. I want to know the probability of getting A12 equal to A no matter what the other components are. So that's the question we're asking. If you are interested in the marginal probability. Yeah. You don't care about the other. Many different configurations will give the same A12.
But of course, you could start with that question. I want to go to this state, to that state. It's not the case here. We're just looking at what's the probability of finding one component of the velocity gradient. We could look at 2 or 3. Okay, since many paths can lead to the same initial and final states, we have to sum over all possible paths. And this can be done by the Martin-Rose formalism, and has been already discussed. And it's very general. You can start with a stochastic differential equation. Here V is the deterministic part of the stochastic differential equation. Here is the prescribed forcing. And okay, to enforce the final condition, we do this by using a Dirac delta function. So this gives a constraint that says that A12 at the final time equals to A. So we look at averages of this. In the limits of a long realization, we expect that we have a stationary stationarity. So rho of A is independent of time. Okay? And here we have the exponential of the action, and this is the traditional Martin-Rose action with P playing a role of an auxiliary variable. Well, the connection with the Freddy-Weizmann theory can be done straightforwardly just by integrating over the variable P. So we end up with an action which depends solely on A. With that, here we have the inverse of the tensor. And in the weak noise limit, when G goes to 0, we expect that rho of A is dominated by the minimum of S. So I of A here, which the minimum of the action, is what's called the rate function in the language of large fluctuation theory. But this is just to make a connection. In my calculations, I work with this Martin-Rose action. Okay? So we are looking at these limits of weak noise, and the configuration that will give the most relevant contribution is the instanton, the configuration which minimizes the action. Okay? So we have to solve the saddle point equations, written like that.
Sorry, you assume that the intensity of the gradient is large. What is the...
At this point, it doesn't need to be large. Our initial motivation was that it's like that. I'm interested in large values of the velocity gradient. But up to now, it can be small and large as well. The main assumption is that the noise must be weak. The weak noise. Okay? I would like to stress that
Sorry, weak noise, just I want to understand. Sorry.
G goes to 0.
Weak noise means Reynolds goes to 0 in the original equations.
No, in the original equation, the Reynolds number is played by tau, which appears in the Cauchy-Green tensor. So indeed, small tau corresponds to large Reynolds number. But you can think, okay, but if you want to do turbulence, you have to decrease the viscosity or decrease tau and decrease G. I know what you're thinking. If you decrease G, you're just going to, you're losing the Reynolds. But at least in principle, you can play a role
So
trying to diminish.
So anyhow, you send the G to 0, but viscosity is kept fixed, or not?
In my calculation, viscosity is kept fixed.
Kept fixed.
But G, actually, I do small but finite G. Okay? I mean that the limit of G goes to 0 is just that when G goes to 0, we know that the instanton is the only configuration that will play a role. For finite G, we know that we need corrections to do that. And I think that Luca will talk about how we go to corrections. Okay, the role of the constraint in the saddle point equations is to set a final condition for P. Right, so we need to solve a mixed initial final condition problem. And so we have to solve A forwards in time while solving P backwards in time. Well, many people try to tackle this problem, and my calculations basically follow this work here. Is the scheme of Chernik-Stepanov, but also Tobias Graf, Hauer Grauner, and etc. Try to solve this problem specifically for the Burger's equation, right? So they were looking for instantons in Burger's equation. And what was found is that shocks amounts to be the instantons in that case. Okay, but the scheme is, just as I said, we need to integrate backwards in P, plug the solution into the equation of A, integrate it forwards, put the solution in the other equation, and wait for it to reach convergence, if it's reached convergence. And here are the results. This is the PDF of the transversal components of the velocity gradient. And the yellow dots correspond to the stochastic the original stochastic differential equation. So that this approach is not valid just for high values of G, but we see that there's a good agreement for small sorry. In principle, we were interested in large values of A, but we see that that the agreement is also well for small values of A. We can obtain the PDFs.
This is, sorry, it's a PDF normalized with the standard deviation? Or with these numbers, 1, 2, what do they mean? They are normalized with the standard deviation?
By the standard deviation, yes, yes. I would say that they're just normal. The PDFs are just normalized.
With standard deviation.
Standard deviation, sorry. Okay, right. Okay.
So these are very small fluctuations. It's order the standard deviation.
Yes, in that case, G is small. To get high fluctuations, we should go to higher values of G, but that's a good point, because for the longitudinal case, we see that there is a disagreement with the Instanton calculations and the PDF of the model. I think that would you like to understand better. Collapse. We can have collapse by rescaling, by performing a scaling transformation, and we see that the collapse is very good for different values of G, and which means that the rate function is independent of G. Well, now I'm going to the analytical results, that we also have some analytical results for the longitudinal case, let's say for A11. And we just noticed that the evolution of the instanton, of the velocity gradient, has just one single degree of freedom. The velocity gradient is diagonal. And it simplifies, of course, the problem very much. And so in this case, we could write the instanton equations for the single degree of freedom. It comes from a Martial-Rose action, but we know that it comes from an effective stochastic differential equation. But this stochastic differential equation can be written as a gradient system. The V of A can be written as a gradient of a scalar function. So in this case, it's much easier to solve the stationary Fokker-Planck equation. And here are the results. We see that the analytical results validate the numerical computation. It sounds interesting. Well, another thing that was performed is that, okay, the instantons, they are good for doing calculations, but what's the role of the instantons in the dynamics of the system? And what we did was this. We performed stochastic conditional statistics. We started with a configuration that at minus infinity, a large time in the past, A was 0, and we performed many realizations and took the case that the velocity gradient, in that case, A12 was equal to a value here, minus 0.25. So it was brute force, the conditional statistics of the stochastic differential equation. We took, after that, the average of these solutions, and it's the green dots. And we just plot here the instanton. for the same final value, and we see that the agreement is very good. So in a sense, the instantons amounts to be an average behavior of the original dynamics. Or you can think that in the limits of weak noise, that the solutions of the equation, they are fluctuating around the instanton solution. So that when you take the average, we have this agreement. Right? And here's the result for the longitudinal component. And in this case, the agreement is not so good, but it was kind of expected since we see this problem in the right tail of the PDF.
You can try to substitute the yellow curve in your action. Maybe try that.
That's the way we got we obtained the PDF.
Oh, the yellow.
Yes.
I mean the clean one.
No. Good idea. We didn't try that. Yeah. Maybe this is the. Yes. With the hope that this is the real instant.
Right.
Well, I think that I finish a bit soon. Here's the summary of this work. I say that the instanton calculation of instanton is not just useful for computing the PDFs or computing the large values, but it also tells us something about the dynamics of the system. We have this idea that the instantons tells the average behavior of the stochastic dynamics. There's a good agreement with the analytics, so it sort of validates the method. Okay, we can also think about applying corrections to that for taking into account higher values of G by doing perturbation theory, for instance. And I think that the next talk will be that. And I would like to dedicate this presentation in memory of Thomas Tangarif. Thank you.